Hi guys, I hope this finds you to be well. We are going to talk about tubular secretion in this particular video. Tubular secretion is the second process that happens in renal clearance. So in order for a drug to be cleared by the kidney, remember in this case there's no metabolism happening, and it's just moving the drug out of the body. So the first way to do that is by being filtered, and we talked about filtration last time, and this is where the drug either is or is not allowed to pass through the glomerulus to get into the tubule. Only free drug will be able to pass through the glomerulus and get into the tubule, because if the drug is bound to a protein, it's too big to fit through the filter. So just think of the glomerulus as a filter and you'll be good. So let's say that now we're talking about the proximal tubule. So it's the next part of the nephron, the tubule, that goes eventually to the bladder and out of the urine. So, oops, I didn't mean to do that. Okay. So, tubular secretion clearance. If you recall, getting back all clearance is blood flow to the clearance organ times the extraction ratio. Remember, each of these is kind of like its own clearance organ. Filtration clearance, the Q is GFR, and the extraction ratio is just the free drug. So filtration clearance is equal to GFR times fraction unbound in the blood. Tubular secretion clearance is also Q times E. This time the blood flow that's feeding tubular clearance, secretion clearance, is our renal blood flow minus our glomerular filtration rate, which gives us our blood flow to tubular secretion, which is about 675 mils per minute. You don't need to know that. I'm just letting you know all the physiologic stuff that goes along with it. So Q is that blood flow to the tubular secretion site times E. Here is our extraction ratio for tubular secretion, and it is dependent upon the intrinsic clearance of the secretion site, how much of the drug is bound, blood flow to the tubular secretion site, which is up here, plus intrinsic clearance of the tubular secretion site times fraction unbound. And again, we can have high tubular secretion clearances where the rate limiting step is blood flow, or low tubular secretion clearance sites where the rate limiting step is intrinsic clearance times fraction unbound. So again, we have this situation. Most drugs are in this situation, although not always. But I'm not going to get into that, but this should look very familiar. It's the same thing as high and low E for hepatic clearance, right? Yes, the same themes keep coming up again and again. You just need to learn a few concepts and just keep reapplying them to really understand a lot about kinetics, which is what I love about it. There's not a lot of memorization. It's really just reapplication of the same theory. You don't have to memorize as much, which is right up my alley. All right, so we know what blood flow is to the tubular secretion sites. It's about 675 mils per minute in a normal person. We know what fraction unbound is, and we know what determines fraction unbound. And we know what determines intrinsic clearance for an enzyme, but we're not talking about hepatic enzymes. We're talking about tubular secretion sites. So what I think of this is here's our blood, and here's our nephron. So the blood there's a membrane in between the blood and the nephron. And what is happening in secretion is drug is moving from the blood into the nephron, from the blood into the nephron. So we're moving drug to the urine, to the tubule. And this is against a concentration gradient, so it can't just be passive diffusion. We need energy, and we need transporters. So in order for the drug to move from the blood to the nephron, it has to be utilizing a transporter. So Tmax in this case is the same thing as Vmax, right? Or N total. So this is the capacity of the system. It's the number of active secretion sites that are available. So how many, I think of these as like little shovels or little Ubers that'll take you from the blood to the nephron. And there's a fixed number of those available. So there's a fixed number of these rides from the blood into the nephron. And the number of those is your Tmax, or the capacity of that tubular secretion system. Then there's also your KTS, which again is analogous to our KM. So this is analogous to Vmax. This is analogous to KM, and it's our affinity. I didn't write that here. It's our affinity, and it's a concentration at which half the secretion sites are available. So at half Tmax, what's the concentration? Again, this is how attracted the drug is to that secretion site. So guess what there's going to be? Competition for those secretion sites. Which means it's a good source of drug interactions. Now, what I mostly want you to know about tubular secretion sites is that we have two types, at least. There's some that transport acids, and there's some that transport bases. So what we know is that acids can only be transported by the acid transport site. And bases can only be transported by base transport sites. So acids will compete with acids. And bases will compete with bases. If you have an acid and a base, they won't compete with each other because they have different Uber rides. Let's say, if we can use today's analogy, maybe we could say that acids take Uber and bases take Lyft, and they don't cross over. So an acid cannot take a Lyft. No. A base cannot take an Uber. No. Acids can take Ubers, bases can take Lyfts. So an acid will not compete with a base for a Lyft ride, and bases will not compete with an acid for an Uber ride. So it's acids against acids and bases versus bases. That's what I mostly want you to know, and this is the biggest source of drug interactions. Couple interesting drug interactions that are used that use this therapeutically. So drug dealers are usually really smart, and they're usually, the brains of the operation is usually a businessman or maybe even a chemist. If you guys have watched Breaking Bad, what they figured out is that some of the drugs of abuse are actively secreted in the urine. So, and let's say that they are a base that is actively secreted. So again, here's our blood. Actually, I'll make that red because why not? Blood. And here's our urine. We may as well make that yellow. Our nephron. Okay, and there's this membrane in between. Now, we have our drug of abuse is actively secreted from the blood. Let's make the drug, a different color, green. the drug is moving from the blood into the nephron and then out of the body, right? But it needs a ride to get out of the body. So what's going to happen if we give another drug, new drug, that is also a base, that is also actively secreted in the urine, but has a lower KTS. So it's got a higher affinity for the transport site. So now our original drug, if our original drug is green, our original drug can't get a ride because our new drug is taking the ride into the urine and out of the body. So if our original drug of abuse cannot get the ride, what's going to happen? It's going to stay in the blood. So there'll be a decrease in the renal clearance of the drug, of our drug of abuse. That decrease in clearance, as you know, will increase our CSS average and increase our half-life. So we're going to get, the drug is going to hang around in the body longer, increasing our CSS average and increasing how long it hangs out. So we're going to literally get a bigger bang for our buck here if we use that. So giving a drug that has a lower KTS will stop our drug from being secreted and it will stay in the blood. Now, this can cause toxicity too. We also use this exact same idea with penicillin and probenecid. Oh, I didn't mean to do that. Shoot. Oh, well. So here's our, So here's our blood. Here's our nephron. And this is making urine, right? So here's our blood. And here's our drug, penicillin, which, as you know, is an antibiotic that is an acid, and it's actively secreted. Okay, so it's moving from the blood, getting a ride, into the nephron and out of the body. If we add probenecid, which I'm going to have a different color, green, I guess. Probenecid. Probenecid is also an acid that is actively secreted, but has a lower KTS than penicillin. So what's going to happen? Now our probenecid is going to say, sorry, I'm now getting the ride because I have a higher affinity. And the penicillin, and I'll be getting the ride into urine to be eliminated. And the penicillin is unable to cross because it doesn't have a ride because the probenecid is more attracted. So the penicillin will stay here in the blood. Thereby, we have a decrease in the renal clearance of our penicillin, which causes an increase in CSS average and an increase in half-life. We use this therapeutically to try to boost penicillin levels in patients with very serious infections or infections in the CNS. So we do use this therapeutically. It can cause serious drug interactions. Obviously, if you didn't want this to happen, you would possibly cause toxicity. And vice versa, if you take away a competing drug that's being secreted. When you stop it, the opposite is going to happen, right? Make sure you understand this because this is a source of drug interactions that are important. That's it.